Hi everyone and welcome to course number 3, E-Motor Production. My name is Moritz Stöckler and I am a research associate at the Chair of Production Engineering of E-Mobility Components at the RWTH Aachen University in Germany. I previously worked in the engineering department at Mercedes-Benz for several years. So much for me in person, let's get right into it. This is module number 3, Rotor Production. The first chapter is called Basics and Product Characteristics of Rotor Topologies. After that, we take a deep dive into the rotor production process. This will be split up into the 3 topologies we see in the market: the permanent magnetic synchronous machine, the externally excited synchronous machine, and the induction machine. To be clear, we use all of these machines as motors, so the name motors or machines are similar. And as you know from the previous modules, we prepared some summary slides in the end. Let's start with basics and product characteristics of rotor topologies. Some things are a repetition of the chapters before, but I think it is a good starting point and helps to remember some informations. Within the electric motor, we have a static, non-movable part, the stator, and a rotational part, the rotor. In the previous module, we have dealt with the stator and the production process. This time we focus on the rotor and again mainly on the production process. If we take a look on the rotor in detail, we notice that the shaft, the bearing system, and some kind of balancing disc are pretty much the same within all electric motor topologies. What's different is the technology of the rotor lamination stack, also called rotor package, which defines the principle of the different electric motors, because the starter can keep the same. A short recap of Module 1 and possibly a few additions to the permanent magnet synchronous machine. We use permanent magnets in the rotor, which give this type of electrical machine its name and keep the magnetic field of the rotor permanently excited. This comes with the disadvantage that no shutdown of the motor is possible and high costs and high dependencies on mining countries. But it keeps the most popular motor type due to its high power density and efficiency. Recap of the externally excited motor. We can easily recognize the rotor windings that replace the function of permanent magnets due to the magnetification of the energized winding coils. This comes with the pretty obvious advantage to refrain from costly permanent magnets, greater functional safety as longer effective operation without overheating, and by that a good efficiency over the operating range we face. The biggest disadvantage is that a slip ring is required to transmit the electrical energy to the rotor, which causes wear and abrasion in the air gap and mechanical wear of the abrasive brushes. The third popular design in the market is the induction motor. And as the name suggests, it works by induction from the stator to the rotor. We use short circuit bars as conductor in the rotor and no coils like in the EESM. We can see that in the picture. The rotating magnetic field of the stator induces current in short circuit bars of the rotor. This generates an opposing field in the rotor which interacts with the one of the stator and generates torque. Because of the minimal time delay of the induction in the rotor is always slower than the stator. This delay is called slip and explains why we talked about synchronous machines in the two designs before. We lack on power and efficiency and have a high demand on the thermal management, but this rotor has the lowest technical complexity and a cost-effective production. That's all for the recap. Coming now to the rotor production process. If we look on the process chain of electric motor production, we dive into the rotor production and see that the balancing and the joining of the rotor package and shaft are the same for all topologies. Due to their individual function principle and the individual used parts and material, the production process for each technology is different, or let's say it better, the production process for each rotor package is different. We find the process steps of the individual rotor topologies on this slide. For the EESM, we need to insulate the rotor slots. We have multiple options in the winding process. Only with the EESM we have an interconnection of the rotor and the assembly of the acceleration system. With the PMSM, it is all about the permanent magnets, how they are assembled and fixed, and how we magnetize them. For the induction machine, we only see the different options to manufacture the rotor cage. The rotor package production or the sheet metal stack production process chain and the respective process technology are largely dependent on the respective rotor topology. Rotor package production is the biggest driver of complexity and will be not explained in detail in this module. But let's jump into it. The first will be the externally excited rotor production. If we look at the shaft manufacture, which stays the same for each rotor type, we can divide between flow forming and machining. The EESM specific process steps can each be done by multiple options. To insulate, we can use the slot-based insulation or the injection molding. For the winding, we choose between flyer winding, linear winding, and needle winding. The interconnection could be done by soldering or hot crimping. The excitation system could be either conductive or inductive. Let's have a look on this in detail. Milling the shaft in production for an electric rotor involves using a rotating cutting tool to shape and finish the shaft. The process starts with securing the shaft material on a milling machine. The cutting tool then removes material from the shaft to achieve the desired dimensions and the surface finish. This is done by moving the tool along various paths, guiding by computer controls or manual adjustments until the final shape is achieved. Milling ensures precision and accuracy in creating shafts that fit perfectly into electric rotors. Flow forming is another metal forming process used to produce shafts for electric rotors. It involves rotating a cylindrical workpiece while applying pressure with rollers to shape it into the desired form. The process starts with placing the workpiece, usually a perform or tube, onto a mandrel. As the workpiece rotates, rollers press against it, gradually thinning and stretching the material into the final shaft shape. Flow forming offers high precision and strength, making it ideal for producing lightweight and durable shafts for electric motors. Now we are starting with the individual rotor package production of the EESM. The first step is to insulate the stack against the wire potential, reducing the risk of short circuits. The process starts by cleaning the slots to ensure they are free from debris. Then, insulating material, such as paper or plastic films, are cut to fit the slot dimension and inserted into each slot base. Of course, we have to keep the insulation paper free from damage and have to take the paper thickness into account in the design of the rotor. Injection molding is an alternative for insulating an externally excited rotor. It involves using a mold to apply insulation material around the rotor components. The process starts with creating a mold that fits the shape of the rotor or its parts needing insulation. Insulation materials, often plastics, are heated until they become liquid and then injected into the mold, covering the rotor components or filling spaces between them. Once cooled and solidified, this created a protection layer that insulates against electrical currents, but we have to keep in mind that this only works in combination with a fixed rotor design and offers limited variant flexibility. Next step is to wind coils onto the rotor by using different methods. One would be the flyer winding. This process involves using a machine called flyer winder, which consists of a rotating arm or flyer that guides the wire onto the rotor, like you can see on the picture. The rotor is placed on the machine, and as it rotates, the flyer moves around it in high speed, evenly distributing the wire from coils. This ensures precise and uniform winding of the wire around the rotor slots. Another method would be the linear winding. The process begins by securing the rotor on a winding machine. The wire is fed onto the rotor and guided along the length in straight lines, creating coils that lay neatly side by side. This method ensures uniform distribution of wire across the rotor surface, maintaining consistent coil tension and alignment. Linear winding is often used for precise applications where neat and orderly coil arrangement is essential for optimal electromagnetic performance. Needle winding for an externally excited rotor involves using a needle-like tool to guide the wire through the rotor slots. The needle carries the wire and moves back and forth through each slot, precisely placing the wire to form coils. This method allows for tight and accurate winding, especially in confined spaces or complex slot designs. Needle winding ensures efficient coil placement, enhancing the electromagnetic performance of externally excited rotors. To summarize the rotor winding technologies, we compare the direct and indirect winding processes. Indirect winding involves wrapping wire around a separated form or bobbin before transferring it to the rotor, for example with the linear winding. This allows for precise coil formation and narrow gaps, but requires an extra step to place coils onto the rotor. Direct winding technologies like the flyer winding places wire directly on the rotor slots, forming coils in one step. It is faster and simpler as it eliminates the need of transferring coils, but may be less precise than indirect methods. Both processes aim to create effective winding for external excitation, with indirect offering precise and direct providing efficiency. Next step is the interconnection of the coils, for example by soldering. Soldering involves joining wires and components by using a solder, a metal alloy. The process begins by cleaning the surface to ensure good adhesion. Then the soldering iron heats the solder until it melts. The molten solder is applied to the connection points between wires or components, creating a conductive bond as it cools and solidifies. Soldering ensures reliable electrical connections within the rotor, supporting efficient current flow and overall performance. The alternative technology for the interconnection is the hot crimping. It involves using heat to secure wire connections with metal sleeves or terminals. The process starts by placing the wires into a crimp sleeve or terminal. A heated crimping tool then compress the sleeve, causing it to shrink and tightly grip the wires, creating a secure mechanical and electrical bond. Due to the fact that the externally excited synchronous machine works by externally excitation to create the magnetic field in the rotor, it is no surprise that we have the assembly of an excitation system as an additional process step. Excitation by induction involves generating a magnetic field within the rotor using electromagnetic principle, where changing magnetic fields induce currents in nearby conductors. This process allows the rotor to be energized without direct electrical contact. The exciter system is then screwed into the internal thread provided in the rotor shaft. Finally, the winding ends contacted in the previous step are connected to the rotating part of the excitation system, and an anti-rotation lock is provided to prevent the screw connection from loosening during the operation. But most of the time we see a conductive excitation system where the rotor is energized via direct electrical contact by the use of brushes. This step involves securing brush holders around the rotor, inserting brushes to contact the commutator or slip rings, attaching springs for consistent pressure, and ensuring all components are firmly fastened. This once again comes with the disadvantage of wear due to the direct electrical contact of the parts. To make this clear, inductive excitation systems uses electromagnetic induction to energize the rotor without direct contact, offering reduced wear and maintenance. Conductive excitation relies on brushes and slip rings to directly transfer electrical current to the rotor, providing efficient energy transfer but requiring regular upkeep due to the mechanical contact. We also see a reduction of installation space through the integration of the inductive system into the rotor shaft and reduction in the number of components. It also enables direct oil cooling. Due to this advantage, it can be assumed that we will face more inductive systems in future. Today we see the well-known conductive system most of the time. The electrical testing of the system will not be part of this module. So that we capture all individual process steps for the externally excited rotor production and move on to the permanent magnet synchronous rotor production. In the production process of the rotor for the permanent magnet synchronous motor, we focusing on the process steps that ensure the magnetic fixation. The shaft manufacturer keeps the same, and the joining of the rotor package and the shaft as well as the balancing we will take a closer look in the end of this module. But the first step is to insert the magnets into the designated slots or cavities on the rotor stack. The process starts by aligning each magnet with its slots, ensuring correct orientation for optimal magnetic field direction. Once positioned, magnets are securely fastened using adhesives or mechanical fixtures to prevent movement during the operation. This precise placement is crucial for efficient rotor function and performance. Once the magnets are placed into the cavities, we need kind of fixation that keeps the magnets in place. As you remember, we have speeds of over 20,000 revolutions per minute. So the process starts with cleaning the surface to ensure good adhesion. Then glue is applied to either the magnets or the slots, and the magnets are carefully positioned into their designated places. Once placed, the adhesive is allowed to cure, securing the magnets firmly in place and ensuring they remain stable during the rotor operation. As an alternative, the magnet fixation can be done by injection molding. This process starts with placing magnets in a mold designed to fit the rotor's shape. Liquid plastics or resin is then injected into the mold, surrounding the magnets and filling any gaps. Once cooled and solidified, the molded material securely holds the magnets in place, ensuring stability and precise alignment during the rotor operation. Another alternative is magnet fixation by expanding coating. It involves applying a special coating that expand to secure magnets in place. The process begins with positioning the magnets on the rotor. An expandable coating is then applied over and around the magnets. As the coating cures, it expands and fills gaps, firmly ensuring the magnets while providing additional protection against movement and environmental factors during the rotor operation. Tesla uses tapping for fixation, using adhesive tape to secure magnets in their slots. The process starts with positioning the magnets on the rotor. Strong adhesive tape is then wrapped around or placed over the magnets, ensuring they stay firmly in place. This method provides temporary fixation and stability during assembly, helping maintain magnet alignment until more permanent securing methods are applied if needed. And last but not least, the quite similar magnet fixation by a sleeve. Magnet fixation by a sleeve for permanent magnet rotor involves enchasing magnets in a cylindrical sleeve. The process starts with inserting the magnets into the sleeve, which fits around them. The sleeve is then positioned onto the rotor, ensuring proper alignment and secure placement. This method provides mechanical support and stability, keeping the magnets firmly in place during rotor operation while protecting them from external forces. As the next step in the rotor package production for the PMSM, we put the substacks together to one complete rotor. The process begins by aligning individual magnet pieces in the correct sequence and orientation. These segments are then bonded or mechanically fastened together to create a unified stack. Once assembled, the substacks is positioned on the rotor shaft, ensuring proper alignment and balance for efficient operation. This method allows for precise construction of complex rotor design using smaller, manageable parts. There are several times when we can magnetize the magnets in the production process. The first would be before assembly them into the rotor stack. So before we start with the magnet fixation. The process starts by placing the magnets in a specialized magnetizing fixture or machine. Then a strong magnetic field is applied, aligning the domains within each magnet to achieve full magnetization. Once fully magnetized, the magnets are carefully handled and assembled into the rotor, but this comes with some troubles. But they should ensure that they retain their magnetic properties for optimal performance during the operation. The other option would be to magnetizing the manufactured rotor. Again, a strong magnetic field is applied, aligning the domains within each magnet to achieve full magnetization. This comes with the advantage that the magnets are not active during the assembly, which make the previous process steps easier. But the magnetic field is weaker after magnetization in the assembled rotor, as the excitation magnetic field is not applied directly to the magnets. Okay, that's all on the PMSM. Now we will look at the individual process steps of the induction rotor cage production. To manufacture the rotor cage, we either use the die casting process step, or we simply plug in bars or rods of copper or aluminum into the designated cavities in the rotor stack. After we cover this in detail, we take a look on the non-specific process steps: joining of the rotor package or stack and the shaft, and the possible balancing technologies. Die casting the rotor cage for an induction machine involves creating the cage using molten metal. This process begins with preparing a mold shaped like the rotor cage. Molten metal, often aluminum, like shown in the picture, is injected into this mold under high pressure, filling its cavities and forming the cage structure. Once the metal cools and solidifies, the mold is opened to release the cast rotor cage. This method ensures precise dimensions and durability, essential for efficient performance in inductive machine rotors. Forming the rotor cage with copper rods for an inductive machine involves inserting copper bars into the rotor slots. The process starts by cutting copper rods to fit precisely within the slots of the rotor laminations. These rods are then inserted into each slot, ensuring they are evenly distributed and aligned. Once in place, the ends of the copper rods are connected or braced to form a continuous conductive path, completing the rotor cage structure. This method enhances electrical conductivity and efficiency in induction machines. All right, now we finished the individual process steps for the rotor package production for the externally excited synchronous motor, the permanent magnet synchronous motor, and the induction motor. Next are the possible techniques to join the rotor and the shaft, starting with stretching. The process begins by cooling the shaft, making it slightly smaller than the rotor's inner diameter. The shaft is then inserted into the bore. As the shaft relaxes, it contracts to form a secure interference fit with the rotor, ensuring strong mechanical connection and alignment for an efficient operation. Shrink fitting is like the opposing to join a rotor package and shaft, also involve using temperature changes to create a tight fit. But this time the process begins by heating the rotor package, causing its bore to expand. The shaft is then inserted into the expanded bore. As the rotor cools, it contracts around the shaft, creating a secure and precise mechanical bond that ensures strong alignment and stability during the operation. Another possibility is pressing in to join a rotor package and shaft. It involves using mechanical force to fit the rotor onto the shaft. The process starts by aligning the rotor bore with the shaft. A pressure machine then applies controlled pressure, pushing the rotor onto the shaft until they are tightly joined. This method ensures a secure fit through friction and interference, maintaining alignment and stability during the operation. Using a feather key to join a rotor package and shaft involves inserting a small rectangular key into a lined slot on both the rotor and the shaft. The process begins by machining keyways on the rotor bore and the shaft surface, or the opposite. The feather key is then placed into these keyways, fitting snugly to lock the rotor in position with the shaft. This method ensures precise alignment and prevents rotational slippage during the operation, providing a secure mechanical connection. So the last step in the rotor production is called balancing. Balancing is necessary to ensure even weight distribution in a rotor, reducing vibration and wear, thereby enhancing performance and prolonging the lifespan of the machinery. We know two ways of balancing. First is the additive step. Balancing a rotor using additives involves applying material to correct imbalances. The process starts by identifying heavy spots on the rotor through testing. Once located, small amounts of balancing compound or weights are added to lighter areas to offset these imbalances. This adjustment ensures even weight distribution, reducing the vibration and enhancing smooth operation during the rotation. The other way around would be balancing a rotor by subtraction. This involves removing material from heavy spots to achieve even weight distribution. Once again, the process starts by identifying areas where the rotor is imbalanced through testing. Material is then carefully removed from these heavier sections, often by drilling or grinding, until the rotor achieves balanced rotation, minimizing vibration and improving operational efficiency. So we cover the complete rotor production process. Let's summarize what we learned today. Starting with some takeaways. first would be that the assembly operations are mainly limited to the actual joining operations. Second, with the externally excited synchronous machine rotors, the greatest complexity driver for the process is the winding process of the rotor windings. Third, the different fixing technologies of the magnets in the permanent magnet synchronous machine rotors are largely responsible for the product properties. So they are very important. Fourth, die casting technologies for the production of inductive motor short circuit cages offers cost potential for large scale production, but it is associated with high investment. And fifth, the core process technologies of the three rotor topologies are the biggest driver of complexity in the rotor production and hold great potential for innovation in the future. Last slide, as always, our summary. In this presentation, the rotor as central subcomponent of an electric motor was explained. In this presentation, the steps in the process chain for the manufacture of rotors for use in traction motors were outlined. In this presentation, winding, magnet fixation, and rotor cage production were identified as key process steps. Okay, that's all. Thank you for your attention. This was the last module of the course E-Motor Production. Have a nice day and goodbye.